Hello and welcome to this introductory video for our data structures and algorithm course. My name is Ali Hassan, and in this course we will be exploring the fundamentals of computer science, diving deep into how data is organized and manipulated. So if you are new to computer science, you might be wondering what exactly data structures and algorithms are. Basically, data structures are the way we organize and store data so that it can be accessed efficiently, whereas algorithms, on the other hand, are the step-by-step procedures we use to solve problems using that data. You might not realize it, but data structures and algorithms are all around us. Every time you use a search engine or browse social media, you are interacting with complex algorithms that help you find what you are looking for. In this course, we will be starting with the basics, building a foundation of knowledge that you can use to understand more advanced topics. We will be exploring different types of data structures like arrays, linked lists, and trees, and learning how to use them to solve problems. We will also be discussing various algorithms like sorting and searching and exploring how they can be optimized for speed and efficiency. And by the end of this course, you will have a strong understanding of the fundamental concepts of data structures and algorithms. In this course, we will be exploring the world of data structures and algorithms. Specifically, we will be looking at how data is organized and manipulated, as well as the logic behind the algorithms used for these operations. Let's start with data structures. A data structure is a way of organizing data so that it can be accessed and manipulated efficiently. Think of it like organizing your closet. You can organize your clothes by type, by color, or even by occasion. Similarly, in computer science, we organize data based on our needs. For example, if we have a dictionary, we can organize it by the alphabet to make it easier to find a specific word. If we have a map data, we can organize it based on its position on the 2D plane. And if we have monthly statements, we can organize it in a tabular form. Data structures provide us with access to the data and the operations that can be performed on it. For example, we can insert data into the structure, delete data from it, and search for data within it. Now let's move on to the algorithms. Algorithms are the step-by-step procedures that we use to perform these operations on the data structures. They are dependent on the data structures we use, as different structures require different algorithms to manipulate them. When we talk about the trade-offs of data structures, we are essentially referring to the fact that each data structure has its own strengths and weaknesses. For example, one data structure may be particularly good at organizing data for quick searching, but not so good at inserting or deleting data quickly. And another data structure may be good at both searching and inserting data, but may require more memory space to do so. Because there is no one ultimate data structure that is perfect for every situation, it's important to understand these trade-offs so that we can choose the appropriate data structure for a given problem. This choice depends on our specific requirements, such as the size of the data, the types of operations we need to perform on it, and the amount of time and memory resources available to us. The trade-off between time and space complexity is particularly important to consider. Time complexity refers to the amount of time it takes to perform a given operation on a data structure, while space complexity refers to the amount of memory space required to store the data structure. Often, there is a trade-off between the two. A data structure that requires less memory space may take longer to perform certain operations, while a data structure that is faster may require more memory space. Therefore, when choosing a data structure, we need to carefully consider the trade-offs between time and space complexity and choose the one that best fits our requirements. By doing so, we can ensure that our code is efficient and optimized for the specific problem we are trying to solve. In order to work with data, we first need to understand what it is and how it's organized, and its most basic level. At its most at its most basic level, data refers to any facts, figures, or numbers that we want to work with. However, in computer science, we often need to be more specific about the properties of the data we are working with. This is where data types come in. A data type specifies the properties of a certain category of data values. This includes the domain of the data or what kind of values it can hold, as well as the operations that can be performed on it. There are two main types of data types: scalar or atomic, and composite or structured. Scalar data types are also called primitive data types, and they have no further subparts. For example of scalar data types, they include integers, floats, and doubles. On the other hand, composite or structured data types have further subparts. Examples of composite data types include arrays, structures, classes, interfaces, and enums. Structs, for example, we are composite data types that allow us to group together related data values. Arrays are another example of composite data types, which allow us to share a collection of values of the same type. In computer science, data structures are a collection of data elements that are organized in a specific way. A data structure can be thought of as a set of rules that define the logical relationships between these elements. Data elements can be either atomic or composite, and they can even include other data structures as well. For example, an array is a data structure that is composed of a collection of atomic data elements such as integers or strings. The structure of a data structure refers to the set of rules that hold the data together, just like how books are arranged in a library or how you organize your music collection. A specific structure can be helpful for certain operations. For example, finding a number in an unordered list can be slow or inefficient process, but if we organize the list in a specific way, such as in an ordered list, we can find the number much more quickly. Similarly, if we are working with a large amount of data, it may be more efficient to organize it using a specific data structure, such as a tree or a graph. Let's imagine that we have a library with a collection of books and we want to perform some operations on this collection. Specifically, we want to find a book whose name starts with a specific word, find all books of a particular subject, and add a new book to the existing stock. To perform these operations efficiently, we need to choose an appropriate data structure. Let's consider three scenarios. In the first scenario, we have an unordered list of books. This structure is simple to implement, but it can be slow and inefficient for searching operations. For example, finding a book whose name starts with a specific word would require us to look through the entire list, which could take a long time if we have a large collection of books. In the second scenario, we have a sorted list of books. This structure is more efficient for searching operations because we can use binary search to quickly find the desired book. However, adding a new book to the sorted list would require us to resort the entire list, which could be time consuming. Finally, in the third scenario, we have a hash table of books. This structure is very efficient for searching operations because we can use the hash values of a book's name to quickly look up its location in the table. Adding a new book to the hash table is also relatively easy because we can simply hash its name and add it to the appropriate location in the table. In conclusion, to choose an appropriate data structure, we need to consider which operations are most important and whether the structure will help us perform those operations more efficiently than some other structure. By understanding the strengths and weaknesses of different data structures, we can choose the right one for a given problem and optimize our code accordingly. In this slide, we will explore different types of data structures and their applications. Let's begin with linear and nonlinear data structures. Linear structures are those in which data elements are arranged in a linear sequence, such as in a stack or queue, whereas nonlinear structures are those in which elements are arranged in an hierarchical manner, such as in trees and graphs. Stacks are used for undo or redo operations in word processors, expression evaluation, and syntax parsing. JVM or Java Virtual Machine is also stack oriented. Queues are used in transport and operations research where various entities are stored and held to be processed later, such as a buffer. Whereas priority queues are used for process scheduling in the kernel, where the priority of a task determines its order of execution. Hash tables are used for fast data lookup, such as in symbol tables for compilers, database indexing, cache, and dictionaries. Trees are used for parsers, file systems, dictionaries such as the one found on a mobile for auto completion and spelling checking, whereas heaps are used for dynamic memory allocation such as in the C++ standard library. And finally, graphs are used for representing connections or relations in social networking sites, routing networks of communication, and data organization. In conclusion, different data structures have different applications, and choosing the right one for a given problem is essential for optimizing and performance of our code. By understanding the strengths and weaknesses of different data structures, we can choose the right one for a given problem and optimize our code accordingly. In this slide, we will discuss the common operations for a data collection and how to choose the right data as data structure based on your requirements. Before we dive into the different data structures, it is important to understand the common operations that we perform on a data collection. These operations include adding a new data, deleting existing data, searching for data, and updating data. Choosing the right data structure. Now, to choose the right data structure, we know the common operations for a data collection. How do we decide which data structures to use? The structure of a data affects the efficiency of data operations, and we need to consider factors like time versus space complexity, generality versus simplicity versus performance, and trade-offs with each data structure. It is essential to note that there is no ultimate data structure that suits all requirements, as we discussed earlier in the previous slides. The choice of data structure depends on our priorities and the assumptions we make about how the software will be used. We need to ask ourselves questions like, does this data structure support the operations I need efficiently? Is it easy to use, implement, and debug? Is ordering more important than anything? In conclusion, data structure is an essential concept in computer science, and choosing the right data structure is crucial for the efficiency and effectiveness of data operations. By understanding the common operations and trade-offs with each data structure, we can make informed decisions and choose the data structure that best suits our requirements. Stay tuned for more exciting topics in this data structure and algorithm course. When we talk about data structures, we are referring to mathematical and logical models that represent the organization and management of data in computer programs. These models help us understand how to store, retrieve, and manipulate data in efficient and effective ways. One important concept in data structures is abstraction. Abstraction is the idea of focusing on what something can do rather than how it does it. In the case of data structures, this means focusing on the operations that a data structure can perform rather than the specific implementation details. For example, consider the data types int and float. Both of these data types take up 4 bytes of memory, but their physical implementation is different. However, from an abstract perspective, we can treat them as interchangeable numeric types that can perform arithmetic operations like addition, subtraction, multiplication, and division. Similarly, we can use abstraction to think about more complex data structures like the account, point, and rectangle classes, or even 2D arrays. By focusing on the operations that these data types support, we can design programs that work with these data types in efficient and flexible ways. One way to take advantage of abstraction in data types is to use abstract data types or ADTs. An ADT is a mathematical model that defines a set of operations that can be performed on a data type without specifying how those operations are implemented. Using ADTs has several advantages. First, it allows us to change the implementation of a data type without affecting the methods that use the data type. This makes it easier to maintain and update our program over time. Second, ADTs provide a common language and framework for discussing and designing data structures. By focusing on the operations that a data can perform, we can compare and contrast different data structures based on their strengths and weaknesses for a specific task. In summary, data structures are mathematical and logical models that help us manage and manipulate data in computer programs. By using abstraction and ADTs, we can design efficient, flexible, and maintainable programs that work with complex data types in powerful ways. In this slide, we will explore more about ADT and how it can be implemented in various programming languages. So an ADT is a data type that defines a set of data values and associated operations independent of any particular implementation. This means that an ADT specifies what a data type should do rather than how it should be implemented. For example, let's consider a stack ADT. It specifies the expected behavior of a stack such as push, pop, and peek, but it does not specify how these behaviors should be implemented. It is important to note that an ADT is the logical view of a data type while a data structure is the physical implementation of it. In other words, a data structure is a way to implement an ADT. So to implement a stack ADT, you will need to choose a container such as an array or linked list and then describe your algorithms for the operations. The choice of container and algorithms greatly affects the efficiency of the data type. In object-oriented programming, interfaces and classes serve as encapsulating units that can hide the implementation of an abstract data type from the user. This means that the user is only concerned about what methods are available and what they do. When a programming language implements an ADT, it adopts a certain implementation logic that can vary from other languages, but the definition of the ADT remains the same. This allows for flexibility in the implementation while maintaining consistency in the definition. In conclusion, ADT is a powerful tool that allows developers to focus on what a data type should do rather than how it should be implemented. It enables flexibility in implementation while maintaining consistency in definition across programming languages.